new video. This is Dr. Muhammad, and this is a new video under the Seismic Design of Structure series. We are still working on this ASCE E7 seismic provisions, and today we're going to talk about three main topics: risk category, importance factor, and seismic design category. So we are going, as usual, we are going to take some examples on each one, and we are going to give the main or the basic concept behind each one of them. Okay, let's start. So this is, as I said, this is the main three items that I'm going to talk about today. Okay. Let's start with the risk category first, and this is the most important item, I guess, before going into the second or the other two items. We want to, first of all, to understand what is the meaning of risk category and why we need it. This part is from ASCE 7, actually it's 16, not 17, sorry for this. So, and the classification of buildings and other structures under section 1.5, you are going to find that it talks about risk categorization. In general, risk categorization, before reading this, I want to highlight the purpose of risk categorization. So the main purpose is to attain minimum levels of earthquake performance deemed suitable to the individual occupancy. Actually, this is an important, we can claim kind of goal for the seismic design codes and guidelines, that we want to attain or at least maintain a kind of minimum level of earthquake performance, okay, or minimum levels of earthquake or seismic performance of the structure. So this is why we need to categorize the structure based on the risk in the first place. This is why we call it risk category. The expected performance of structure is controlled by assignment of each structure to one of four occupancy category. We're talking here actually about like occupancy categories. Based on the occupancy of the structure, we can assign it to a certain level among one from four different levels. ASCE provisions specify progressively more conservative strength drift control, system selection, and detailing requirements for structures assigned to higher occupancy groups or risk categories. Whenever that we have, the point is, whenever we go in the levels or categorization of the risk categories, we're going to notice that ASCE provisions are giving some controlling requirements like drift control or specific system selection that you should choose, or specific detailing requirements. So this is going to be based on the, as I said, the minimum performance level that we try to maintain in our structure. In terms of post-earthquake recovery, certain types of occupancies are vital to public needs, and this is an important issue. We cannot like make two buildings. One is going to be used as a shelter after earthquake, with another building that is only used during some period of the time or some period of the year, and it is not used after the earthquake as a shelter. So based on this, we need to distinguish between different buildings based on their occupancy and based on the risk that we want to highlight whenever that they are going to be used, whether during earthquake or after the earthquake. Now let's go back to this definition that is given by the code. So buildings and other structures shall be classified based on the risk to human life. That's the word risk that has been used here. So we are categorizing them based on the risk to human life, health, and welfare associated with their damage or failure, by nature of their occupancy or use. That's the point. This is why the word occupancy category has been mentioned in the previous slide, or the slide that I've explained shortly, or use. So we are talking about the occupancy. What is the type of occupancy or the use that we are going to, this structure is being used for. According to table, we're going to look at this table 1.5-1 for the purposes of applying flood, wind, snow, and earthquake and ice provisions. So if we're going to take a look here on this table, so we're going to see this is the table 1.5-1. This is in chapter 1 in ASCE. It is giving to us risk category of buildings and other structures for flood, wind, snow, earthquake, one of them, and ice loads. Okay, now let's go back again. So again, I want only you to remember that the word risk here, why we have used it in the title. Okay. Each building or other structure shall be assigned to the highest applicable risk category or categories. Why it is the highest shall be assigned to the highest? Because maybe you're going to find that the same building is assigned to different risk category. So you are going to choose which one that it should belong to. So we are going to choose the highest one. Okay? If there are two approaches that is at the end going to give us different risk category, we should take the severe. Okay? The most severe case or categories. Minimum design loads for structures shall be incorporate the applicable importance factors given in table 1.5-2. We are going to, this is actually talking about the importance factor, which is something I'm going to touch upon after a few slides from now. Assignment of a building or other structure to multiple risk categories based on the type of load condition being evaluated. Okay, so we are talking about seismic in our case. Okay, shall be permitted means that we are talking about seismic, not snow, not ice, or not wind or flood. When building code or other referenced standard specifies an occupancy category, that's the word occupancy category here, the risk category shall not be taken as lower than the occupancy category specified therein. This means that in other reference standard sometimes in other references they are taking the word occupancy category. Okay, so if we are going to use this word, this term occupancy category, here the code is telling us that when the building code or other referenced standard specifies an occupancy category, the risk category, which is in our case in our standard ASCE, the risk category shall not be taken as lower than the occupancy category specified therein. So we are taking the most severe case from the occupancy category here, or from the risk category that is in ASCE 7. Okay, now let's have a look on the table. This is the table. You can find it on ASCE, and the name of the table is risk category for buildings and other structures for flood, wind, snow, and earthquake, which is our main concern, and ice loads. In the left column, you are going to find use or occupancy of the building structure, and in the right hand side we are going to find the risk category. So we're going to find that we have like 4 different risk categories, 1, 2, 3, and 4. So we're going to find they are different. They are being used in different ways. I'm not going to read everything, but just risk category, for example, 1, it is for buildings and other structures that represent low risk to human life in the event of failure. It's a little bit generic, not very clear, right? And this is why we are going to find that in other reference, for example, in I, B, C, in International Building Code, they are giving much more details actually compared to ASCE regarding the occupancy in building, use and occupancy of buildings. And risk category 2, it is all buildings and other structures except those listed in risk categories 1, 3, and 4. So here, this is all buildings except what is going to be listed in 1, 3, and 4. Let's talk about, for example, 3 here. This is risk category 3. Buildings and other structures, the failure of which could pose a substantial risk to human life whenever there is hazardous material, for example, in one building, and it's going to make a substantial risk to human life. This is considered to be risk category 3. We're going to take some examples, and you're going to find that it is based on the structure and its use. So it is going to be clarified for us using some examples. Another type is buildings and other structures not included in risk category 4, which with potential to cause substantial economic impact and or mass disruption of day-to-day civilian life in the event of failure. Okay, so we are going to find that there are some buildings, they are important they are not in seismic category 4, but as they are saying here, that their damage would cause a substantial economic impact and or mass disruption of day-to-day civilian life. Okay, so that's important for us also to take care of, and these kind of buildings we need to assign it to risk category 3. For risk category 4, it is buildings and other structure designated as essential facilities. It is essential facilities. Okay, the failure of which could pose a substantial hazard to community, buildings and other structures, including but not limited to facilities that manufacture, process, handle, store, use, or dispose of such substances as hazardous fuels, hazardous chemicals, or hazardous waste. So these are anything that is very critical, like hazards. Okay, hazardous material, then it is considered to be from category 4. Okay, now let's go to see what is the usage of the risk category itself, why we are going to study and why it is going to be important for us. Risk category is used in several places in ASCE. Okay, so the requirements based on risk category, you are going to find it in different spots in the document, including determination of importance factor, which we're going to study in a minute. Okay, importance factor, we're going to find it in section 11.5.1 and table 1.5-2 as mentioned before. So the determination of importance factor is highly linked to risk category. Requirements for protected access for risk category 4 structure, which is going to be in section 11.5.2. Determination of seismic design category, which is something we're going to talk about in a minute, and which is going to be under section 11.6 and table 11.6-1 and 2. And determination of drift limits, that's very important as well. We're going to find it in chapter 12, 12.12.1 and table 12.12-1. Okay, so these are the direct requirement that is related to risk category or risk categorization. Okay. Okay. Now, in table 1.5-1 provides general description for all risk categories, which already we have read from, and we can briefly we can put it like this. The risk categories range from 1 to 4, and for 1, which is the first or the low risk, it is considered to be low risk buildings and other structures that represent a low risk to human life in the event of failure. That's in general. Okay, and for risk category 4, buildings and other structures that are designated as essential facilities and or pose a substantial hazard to the community in the event of failure. Okay, and in between is going to be risk category 2 and 3, of course. Okay. The broadness of the risk category description in table 1.5-1 makes the table insufficient for classifying risk in most cases. That's what I have mentioned before, and I have noticed that it's a little bit broad and a little bit generic in table 1.5-1. We need to know specifically what is the name of the building, what is the number of or capacity, okay, of this building, okay. So that's why it is actually not sufficient. This table is not sufficient for us to judge the building. More detailed descriptions of risk category are provided in table 1604.5 of the 2012 International Building Code, ICC 2011. I think that we have now ICC or IBC, which is more recent. We are in 2020 now. So I think that the most recent International Building Code is going to give us more detailed description regarding risk category. Okay. In several cases, the IBC risk category descriptions refer to occupancy groups. They call it occupancy groups. Specifically, occupancy group 1, which is used for institutional facilities. This is very important and informative for us. If you are going to look to this table, okay, you are going to find that it's very informative, going to give you some different capacities in terms of the occupants of each building and the institutional facilities. These groups, which are defined in section 308 of the IBC, are further subdivided into 4 separate subgroups as follows. So in IBC, you are going to find that different 4 groups under, as we said, the first I, which is the group 1, occupancy group 1. Okay, so we can say that we have group I1, I2, I3, and I4. I1, structures or portions thereof for more than 16 persons. Now it is more, I think, more specific, right, compared to the ASCE. So this is something that you should keep in your mind, that IBC is better in terms of more details regarding the occupants and number of occupants, who reside on a 24-hour basis in a supervised environment and receive custodial care. Examples include assisted living facilities and convalescent care facilities. And 2, the subcategory 2, buildings and other structures used for medical care. So medical care is considered to be from under this group on a 24-hour basis for more than 5 persons who are incapable of self-preservation. Examples include hospitals and nursing homes. That's an important issue. Now, for us, we can highlight this based on the number and the type itself, like hospitals and nursing homes. This is actually examples, but mostly we are going to have where we are going to find like persons who are incapable of self-preservation. Okay. And subcategory 3, buildings and other structures that are inhabited by more than 5 persons who are under restraint or security, like jails, for example, or prisons. Examples include detention centers, jails, and prisons. Buildings and other structures used for day care, where more than 5 persons or any age receive custodial care for less than 24 hours per day. Okay, these are the categorization. Okay. Additionally, several of the risk category descriptions in IBC, table 1604.5, depend on the occupant load. That's an important term that you are going to find many times. Occupant load of the building. Okay, so the meaning of occupant load is the number of persons for which the means of egress of the building or portion thereof is designed. Okay, so this is actually in chapter 2 of IBC, defines the occupant load. Okay, as this is the definition of it. Okay. Occupant load is determined in accordance with chapter 10 of the IBC. Number of persons for which the means of egress means that like exit, okay, or way out, okay, of a building or portion thereof is designed. Occupant load is determined in accordance with Chapter 10 of IBC. So you can visit Chapter 10 of IBC. In the following exercises, we are going to take several exercises. An example, the use of Table 1.5-1 of ASCE in conjunction with the Table 1604 of the IBC is demonstrated through several scenarios. The following example demonstrates the selection of risk category for variety of buildings and other structures. Let's have a look here. So this is example 1. A dockside cargo storage warehouse, take care, so it is warehouse adjacent to Houston Ship Channel. The building is 1 story with a gross floor area of 30,000 foot squared. Cargo is transported by forklifts and overhead cranes and is moved in and out daily. Take care of this, moved in and out daily. Okay, these are like key words for your warehouse and day in and that moved in and out daily. The cargo may contain materials, and it's important one. What is the type of the material? Certain liquids in metal drums considered toxic. Okay, this is another issue that we should consider to humans. So it is something hazardous material, right? The occupancy load, as we have understood now, it is 60. Now, so this is the description. We are talking about warehouse, that it's the forklifts and overhead cranes, they are moving in and out on a daily basis, and it contains toxic material. So if we're going to look to our table, the word toxic material, okay, and warehouse and something that is working in and out on a daily basis, then this gives us like some clues where that we are going to choose it. Explanation first before going into this, before giving the answer for this. Actually, the risk category is going to be 3. Why? Although the principal use of this non-essential, take care, it is non-essential, as we said, it's dockside cargo storage warehouse. It's non-essential facility, is storage. Significant human activity takes place in the structure. So risk category 1 is not appropriate. Do you remember that risk category for very low risk buildings or structures? Our case it is because we have like human activity takes place there. There are some people there, right? And the storage of toxic materials generally requires risk category 3. Do you remember that? We said that storage of toxic materials needs risk category 3, and this is true. Okay, take care between storage of toxic materials and the hazard, or we can say that the release of this toxic material itself going to pose some threat on human being and public or not. That's an important issue. So maybe it is toxic material, but if it's going to be released, it's not going to pose any kind of threat on the public, right? Take care of this. However, according to section 1.5.3 of ASCE and similar language in footnote B of the IBC table 1604.5, the structure may be classified as risk category 2 if a hazard assessment and risk management plan can demonstrate that the release of toxic materials does not pose a threat to the public. That's the issue here. Okay, so our case, based on this discussion, we can understand now that our risk category in general, it is risk category 3. It is not 1 because it's not low risk category. It is not 4 because it's not essential facility, very essential facility. So it may be 2 or 3, and between 2 and 3, and we said the discussion here and the justification here. Okay, so that's the point. Risk category 2 if a hazard. So the structure may be classified as risk category 2 if a hazard assessment and risk management plan can be demonstrated. Actually, we didn't mention about any kind of hazard assessment and risk management plan here, right? It's only dockside cargo storage. It's not going to make anything, or I don't think they are mentioning actually there is no hazard assessment here. Okay. Okay, now let's go to another example. Let's go to another example. The entry foyer for a regional hospital in St. Louis, Missouri. The 1,800 foot square glass enclosed structure is separate from but adjacent to hospital. Take care, it is adjacent to hospital. The main purpose of the foyer is for visitors to the hospital to gain access to the main hospital building. A reception desk and several unattended information kiosks are also in the foyer. A covered walkway passes between the main hospital and the foyer. Hospital staff and emergency personnel gain access through other portals. Okay, so actually if you look here to this one, it is adjacent to a hospital. Okay, so let's read the explanation before assigning the risk category. The hospital is clearly a risk category 4. Without a doubt, we're talking about hospital, and this is considered to be part of it, right? If the foyer were an operational entry into the hospital, so section 11.5.2 of ASCE would require the foyer to be classified as risk category 4 as well. However, because hospital staff and emergency personnel do not take care of this, do not gain access through the foyer, the entry foyer may be considered non-operational and take care of this word, non-operational, and hence may be classified as risk category 2. Okay, it is going to be, why it is risk category 2? Because it is not in 1, not in 3, not in 4. Okay, consultation with the local building officials would be appropriate before a final designation could be made. But if I am a designer and it is near to a hospital, okay, then in this case we can say, risk category 2 is okay for us. But I want to be sure that our building is not going to pose any kind of threat on the hospital. So I can choose in this case risk category 4. Okay, as I said, this decision should not be taken by the structural engineer only. It should be taken by other officials and even including the owner, okay, of the building. Okay, last two examples, I want to go through them quickly only for you. It is going to be risk category 2, an affiliates office building, CBS News affiliates office building in Florida that contains 2 studios for broadcasting local news. The facility is not designated emergency communication center. The occupancy load is 235. This is directly, it is going to be risk category 2. Yes, selected. This is selected because the building is not designated as an emergency communication center. So it is not going to be 1, it is not going to be 3, it is not going to be 4. Risk category 4, okay? Here also a 3-story university office, classroom and classroom building in Virginia. The occupancy load is 375. Risk category 2, this is going to be risk category 2. Was chosen here because the building has an occupancy load of fewer than 500. This is an IBC. There is a limit with the 500. So this means that it would not go to risk category 3, for example, which is the threshold or for classifying the building as risk category 3. So between risk category 2 and risk category 3, there is a limit, a threshold here, which is 500 occupants. If it's less, then it is going to be 2. If it's larger than 500, it is going to be 3. Okay. Note that a high school, secondary school building with an identical configuration would have risk category 3 because the occupancy load is greater than 250. Take care, we're talking about 3-story university office, okay, and classroom buildings. If it is a secondary school, okay, secondary school, maybe you say that it's educational institution similar to this, okay, but here in secondary school, like high school, like massive students, they are going to use it, so the threshold is 250, not 500 in this case. Okay, anyway, they are giving to us, there are numerous examples. We cannot like exhaustively find all the examples, but it is only a kind of indication for us. Okay, now let's go to the second part of this video which is related to the importance factor and seismic design category. Okay, now let's go to the importance factor first. The importance factor, you can find it under section 11.5, importance factor and risk category. An importance factor, IE, it is called IE. Okay. Before it was I only, right? But now they are putting it, we want to distinguish it among the wind and ice and flood, so they put E for earthquake. Shall be assigned to each structure in accordance to this table. So we have this table, which is 1.5-2, importance factors by risk category for buildings and other structures for snow, ice, and buildings. So we are talking about this seismic importance factor, i.e. here. Okay, and they are going to be, as you can see here, based on risk category. Okay, from the table 1.51, we are going to assign it 1 here, 1.5, 1.25 for risk category 3, and 1.5 for risk category 4. As we said before, that the assignment of the importance factor, i.e., is not the sole responsibility of the structural engineer. It is decision to be made concurrently with the building owners, architect, and the building officials. Okay, so we need to be careful. This is, maybe we cannot decide it directly. Okay, we need to have the help from officials, building officials, and architect, and maybe the owner. Okay, so now let's go, what is the importance factor is all about? Why we need the importance factor? Okay, actually the importance factor is to improve the capability of certain types of buildings, such as essential facilities and structure containing substantial quantities of hazardous materials, to function during and after design earthquakes. Actually, whenever that we have, as you said, that we as we have seen that it is, we have 1.25 and 1.5 importance factors for risk category 3 and 4. This means that for these kind of risk categories, we need to give more load for design of the structure itself. This means that we are going to make it behave elastically during the earthquake. That's a very important concept. Whenever that we increase the response or the importance factor, this means that the design load on the structure is going to be increased, and then the structure is going to be maintained within the elastic range. We would not let it go into the inelastic range, okay, by making the sections to be massive, for example, and make the load and the design load to be higher. This is achieved by introducing an importance factor of 1.25 for risk category 3 and 1.5 for risk category 4. This factor is intended to what? Reduce the ductility demand. What is the meaning of this? If we look to the structure itself, this is the common pushover curve of the structure. Okay. If we are going to multiply the design force by IE, which is 1.5, for example, we're going to find that the structure is going to behave something similar to this. Okay. What did I mean? Look to this point and look to this point. This is what we call it the ductility demand, the maximum. If we say that this is the point where the earthquake is going, or there is earthquake demand, it would be here for this case of the original structure without multiplication of the importance factor, and it will be here, which means that less ductility demands on the structure. But you're going to find that it has what? Higher forces. There are more forces. We need to design our sections to resist more forces. Okay. When combined with more stringent drift limits, okay, the results is improved performance of such facilities. We are going to use it sometimes with more stringent drift limits, and this is something the code also can apply and pose on the structure. Okay. Now, the main idea of the importance factor, you're going to find that importance factor is being used in chapter 12 in ASCE, and the factor that is the response coefficient, CS, okay, and it is going to be you are going to find it like this, SDS over R over IE. It seems as if that we are like controlling the response modification factor. Maybe you do not understand now what is the meaning of response modification factor. It's not important, but it is a factor that is taking into consideration the energy dissipation of the system or the lateral resisting system. So actually here, what we want to say that IE does not have any relation with the system itself, okay? Or even when we go to this equation, for example, we're going to find that IE and in the numerator, not denominator, as if that it controls the SDS. But actually it has nothing to do with SDS as well. Importance factor, let's see, importance factor are a function of the risk category and are provided in this table. So it is function only on the risk category that we are going to assign for the building. Values range from 1, okay, to 1.5, as we said. The primary use of importance factor is in the determination of design lateral forces. This is its main, as we said, this is the main purpose. The design lateral forces, okay? So that's why we use it for, in order to increase the design lateral forces and make the structure to be like behaving elastically during the earthquake. Okay, in equation 12.8, which is this equation, as we said, it's only a note. IE appears to be modifier for R, which is not incorrect, which is an incorrect interpretation, because R is a system-dependent parameter that is independent of risk. So you should look to IE in this equation or in this equation independently. It has nothing to do with SDS. It has nothing to do with R. Okay. Okay. So the true purpose of the importance factor is to provide an additional strength for risk-critical facilities. That's it. So whenever that I ask you about what is the main purpose of the importance factor, so it has nothing to do with SDS, it has nothing to do with R, but it is only for providing an additional strength for risk-critical facilities. Okay. Okay. For the same level of ground motion and type of detailing, a stronger building will have lower ductility demand and less damage than a weaker system. That's exactly as I said. Exactly as I mentioned for the example that I said, this is, we have like different buildings like this. This means that more ductility demand. Here this means that less ductility demand. This one is delta, which is the deformation, and this one is the base shear that is going to be developed. Okay. So when we improve or give more importance factor or higher importance factor, we are decreasing the ductility demand. Okay. The comparison of the system behaviors with different importance factors is shown through a set of idealized force deformation plots. In this figure, we have different force deformation plots. This is the horizontal axis, is the relative displacement. The vertical one is relative seismic base shear. So as you can see, if we use importance factor 1, more ductility here, as you can see, it is more ductility here, demand. Here 1.25, the base shear is increasing, as you can see, because this is the relative seismic base shear is increasing. The ductility demand is less, and if we use 1.5, ductility demand is less and less, but the base shear is higher. So we have, this is the meaning of the importance factor, how it will change our capacity curve or the pushover curve. The comparison of systems. The risk category for building with IE 1.5 would have a significantly lower ductility demand. That's here, 1 for example. And probably would sustain less damage than the system with only 1. That's right, less damage because the drift is going to be less. Damage is reduced but not eliminated. Still, we have some drift here. Okay, there are some drift here. Okay, this is the value, but it's not eliminated. Just we're reducing. Okay, and risk category for systems. Okay, that's the meaning of this one. Now let's go to the seismic design category. Seismic design category, you're going to find it in the code under section 11.6. And sections or structures shall be assigned seismic design category in accordance with this section. Risk category 1, 2, and 3 structures located where the mapped spectral acceleration, response acceleration parameter 1 second and period, and S1 is greater than or equal to 0.75 shall be assigned to a seismic design category. Now I'm going to read it after giving first what is the main concept and the purpose of the seismic design category. So ASCE established different SDCs, which is seismic design categories, that are the keys for establishing design requirements. So it is going to give us the design requirements for the building. It is going to tell us what is the limitation of the height of the building, what is the type of detailing, what is the limitation of the drift, what is the threshold for some certain parameters, what are the type of detailing as we mentioned, what is the type of analysis that we should use for the analysis. So it is very important, very important. Okay, the SDC, for example, A, so we are giving like different, we have like A, B, C, D, E, F. You can tell that if we're going to start with A, this means that very low seismic design category, and there are no such stringent requirements for it. But if you go to seismic design category F, oh, it is very stringent. Requirements is going to be there. So we are having a kind of range between them. So we have A, B, C, D, and F. Okay, so it is going to be established using short period and 1 second period response parameters. It is based on SDS and SD1 and the occupancy category, which is the risk category here. Okay, it is the risk category. So we have like SDC-A, SDC-B, SDC-C, and D, and we have E and F. We have E and F. Let's go here and read this. Seismic design category A represents structures in regions where anticipated ground motions are minor, even for very long return periods. For such structure, ASCE 7 requires only that a complete lateral load resisting system be provided and that all elements of the structure be tied together. That's it, which is, we call it the lateral load. Okay, resisting system should be what? Yes, tied together. Just to be tied together. There is a continuous path. Okay. A nominal design base shear equal to 1% of the weight of the structure is used to proportion the lateral system. So it is not big deal here, as if that it is waived from the earthquake requirements. So only we are going to design the structure for 1% of its weight. If we have the weight of the structure, then 1% is going to be applied to design our structure, lateral load resisting system. If we're going to B, C, D, then we are going to have more, okay? It is more serious for us. For B, for example, it is for structures in regions of seismicity where only moderately destructive ground shaking is anticipated. In addition to the requirements of A, structures seismic design category SDC-A, structure in SDC-B must be designed for forces determined using, yes, actually this is part from ASCE 705, but anyway, we should use our the latest one, okay, seismic maps. Okay, so this is actually from seismic design category, for seismic design category B. Okay, and for CSDC includes buildings in regions where moderately destructive ground shaking may occur. The use of some structure system is limited. Here, some lateral resisting systems are going to be limited. Not all lateral resisting system systems are available for us. And certain non-constructor components must be specifically designed for seismic resistance. So now we go more stringent and stringent. For SDCD includes structures located in region expected to experience destructive ground shaking, but not located very near to the major active faults. Actually, we end at D, where that we are far from the earthquake source. Starting from E and F, we are going to get closer to it. Okay, so here for very near major active faults, this is not for our D. It is not located in this in the vicinity of the earthquake fault. In SDCD, severe limits are placed on the use of some buildings. Actually, it's not. It's maybe part of the wording is not highlighted here. But anyway, we understand that there is some severe limits would be placed on the use of some buildings. Okay. For seismic design E and F, it includes structures in regions located very close, take care, very close to major actives like San Andreas, for example, fault. And SDCF includes occupancy category for structures in these locations. So here, SDCE, it is in vicinity of earthquakes, but SDCF, it is more severe. That is the buildings with risk category 4. This means that SDE, if it's risk category 1 or 2 or 3, but here F, it is for risk category 4. Very severe limitations on systems, irregularities, and design methods are specified for E and F. That's right, SDC, E and F, very limited. You are going to find they are not accepting lateral resisting systems in many cases, only nonlinear time history analysis, drift limitations are very stringent, and so on. Okay. For the purpose of determining if a structure is located in a region that is very close to a major active fault, ASCE uses a trigger of mapped MCE spectral response acceleration at 1 second period, S1 of 0.75 G or more, regardless of the structure fundamental period. Okay. Actually, this part, because this is, as I said, it is related to ASCE 705, okay, and maybe also for 10. They were like didn't put a kind of limitation or requirement for knowing whether that the region is near fault or not. But starting from ASCE 716, they put. Do you remember that in the previous video I mentioned about that near fault and far fault? So now this part, it's considered to be history of the this seismic provision itself. They were using S1 greater than 0.75, as we are going to see in our examples. Okay, that if the mapped maximum considered earthquake, and also they used only maximum considered earthquake, not risk targeted. I'm sorry, because this is actually based on ASCE 7-05. Okay. So this kind of description, but actually now we can work with ASCE 7-16. So we can now get whether the region or whether the structure is located near or far fault. Okay. Seismic design category exception for buildings with very short periods. Under certain circumstances, determining the seismic design category on the basis of SDS only is permitted. The specific requirements are listed as 4 numbered points in 11.6. Actually, as we said before here, it's supposedly to be based on, the designation should be based on SDS and SD1, right? But it is allowed to use SDS only, okay, under some specific requirements. All of them, they are talking about this provision applies only for system with very short periods. That's the case. very short periods with approximate TA less than 0.8 TS. This exception, where applicable, may result in lowering the SDC from, say, C to B, for example. Okay, so this is only for what? Short period structures. Short period structures. Okay. Okay, now let's go to the to see it itself. So here, seismic risk category 1 to 3 structure located where the mapped spectral acceleration, response acceleration parameters 1 second period S1 is greater than or equal to 0.75 shall be assigned to seismic design category E directly. And risk category 4 structures located where the mapped spectral response acceleration parameters 1 second period S1 is greater than or equal to 0.75. Take care, we're talking about S1 directly here, shall be assigned to seismic design category F. Okay, so now this is the case for seismic design category E and F. Okay, so for 1, 2, 3 structures located where the mapped spectral acceleration is greater than or equal to 0.75, then in this case we are going to seismic design category E and F. Okay, all other structures shall be assigned to a seismic design category based on the risk category and the design spectral response acceleration parameter SDS1 and SD1. So for E and F, we are taking exactly S1 as our main parameter for designing or for assigning E and F. Why? Because we think that spectral acceleration at long period, means that 1 second or more, is more relevant to near fault, not S sub S. Okay, not S sub S. S sub 1 would be more relevant. And we said that E and F, they are going to be for E and F, they are sensitive to this. We are going to consider for the near fault cases. Near fault cases. So S sub 1 is a good parameter for the near source buildings, not S sub S. So this is why they are talking about 1 second period S sub 1 to designate E and F seismic design category. However, for our all other seismic design category, we use the SDS and SD1 as you are going to see in this table. So we're going to find that we're going to have two tables, 11.6-2-1 and -2. This is for short period and this is for 1S period. SDC based on short period response acceleration. So we are going to find that categorization for SDC here and risk design risk category 1, 2, 3 or 4. Similar here 1, 2, 3 or 4, and here the categorization of SD1. Okay, if we're going to this table and this table, and we found that the risk category, for example, here it is B, however here we found it D. So which one that we should use? We should use the severe one, which is D. Okay? Okay, the parameters that affect SDC are the risk category, as we said, and the design level spectral acceleration, SDS and SD1, as we said, SDS and SD1. Or for very high level ground motions, the mapped maximum considered earthquake MCR risk targeted spectral acceleration S sub 1 should be used, as we said. Okay, for very high it is for E and F. There should be used. Even that E and F, they are not here in the tables, so you're not going to find them because they are not going to be designed using SDS and SD1. They should be used S1. Okay, S1. This is the mapped. Do you remember the first lecture that I was talking about this, the mapped one? We have the mapped acceleration, we have the maximum acceleration or spectral acceleration, and we have the design spectral acceleration. Here they are using the design spectral acceleration, but here we are using the mapped one. Okay, The SDC depends on the site class because SDS and SD1 are directly related to the site class via equations. Do you remember these equations? So we have, this is the design. Actually, no, this is not the design, this is the maximum spectral acceleration. This one is the mapped spectral acceleration from the maps directly. It should be noted that each building shall be assigned to the more severe SDC in accordance with the table. As I said, if you find a D here and B here, then you should use D. Okay, I have explained. Let's have an example and wrap up this video for today. This example from Seismic Design Manual. Okay, Seismic Design Manual, I guess 2012. It is under IBC 2015. So they were talking, or they have issued some edition that is using, this edition was under IBC 2015, I guess, and it is under Volume 1 Code Application Examples. Okay, Code 1. So it is IBC 2015. Okay. Seismic, remember, Seismic Design Manual. So I didn't find any electronic copy of it, so I had to like take pictures by myself and put it here. So it's a little bit wavy. So sorry for this, but I have no other options. So in this design, we're talking about the importance factor and risk category, seismic design category, 3 of them. Let's have the problem itself. There are 2 private high school. Take care, it is high school. Buildings each have an occupant load greater than 250. Take care of this. And the following design spectral acceleration parameters are provided. SDS, it is 1.17, SD1, 0.75, S1, it is 0.75. Take care of this. S1, 0.75. Only I'm going to revisit something important that you are going to understand what I'm talking about for 0.75. Yes, this one. Do you remember this? 0.71 for S1. Take care of it. Okay, so we have explained, but I'm going to highlight it again in the example. One building is a traditional classroom wing. The other building is a gymnasium designed as an emergency shelter. So we have classroom, a classroom wing, and the other one is gymnasium. Determine the following: risk category and seismic importance factor for each building. And number 2, seismic design category SDC for each building. So we need the risk category, importance factor, and SDC. Okay, let's jump into it directly. For risk category and seismic importance, we need to go and visit table IBC, table 1604.5. That please revisit it or visit it on IBC. Risk category of buildings and other structures. The risk category for a private high school classroom building with an occupant load greater, take care, it's greater than 250 is risk category exactly 3. It is not 2. If it's higher than 250, we're going to be a risk category 3. The risk category is used to determine the seismic design category in accordance with section 11.6 in ASCE. For a gymnasium, so in this case, our classroom, this is the occupancy, risk category, it is going to be 3, not 4. Okay? And for a gymnasium that is designated as an emergency shelter, this is emergency shelter. So now we can directly say it is exactly seismic risk category 4, number 4. It is the highest level. So it is gymnasium and is going to be emergency shelter. So it is going to be 4 here. The importance factor for seismic loads from the table 1.5. Do you remember that? We have for risk category 3, it is 1.25. For risk category 4, it is 1.25 for risk category 3 and 1.5 for risk category 4. Okay. Now let's go to the last thing, which is seismic design category. Actually here from the table, we know the occupancy here, this category already we have obtained it, and 1.17 it's SDS. If you visit table 11.6-1, you're going to find that SDS is higher than the threshold, right? Let's go here and see this. So from the table, SDS, it is higher than 0.5, so this means that D, right? And if you go and visit this again, we have for SD1 it was 0.75, right? It was 0.75 here, so let's visit the table and see SD1, it is 0.75, so we are higher, we are D, right? Okay, so this means that we are here. Okay, so we have SDS 1.17, it is D, and SD1 it is 0.75, so it is D. So we should say it is D, right? No, it's not right. Take care of one thing that I have mentioned to you, that S sub 1 equals to what? Equals to what? 0.75. Exactly. This means that it is very high seismic zone. And in this case, we need to visit the table. Note that for risk category 1, 2, 3, having S1, take care, S1, not SDS or SD1. It is S1, mapped maximum considered risk targeted acceleration, larger than or equal to, we are in equal to 0.75. Recall it is S1 equal to 0.75. The building shall be assigned to SDCE. That's right. Right? Also for risk category 4, yes, this is for all these risk categories. If S sub 1 is larger than 0.75, then our SDC should be E. If we have risk category 4, like our gymnasium, then having S1 larger than 0.75, the building shall be designed to SDCF. So it is F. So the classroom would be E, not D, and the gymnasium would be F, not D also. Okay? So that's very important, and this highlight the importance of this part that we were talking about. Take care of this. 0.75. Okay, if it's E, if for S1 it is going to be E for all risk categories 1, 2, 3, but for risk category V, risk category V, it is going to be F if we have the spectral acceleration to be 0.75 or larger. Okay, okay. This actually ends our today's lecture. I hope that you have understood it well, and I hope that you go through the tables that I have mentioned in this video. Thank you very much, and see you in the next video.